Hello guys, welcome to this video. I want us to discuss this. You have the behavior of a damped harmonic oscillator described by this differential equation, and we want to describe the solution as k increases. So k is a damping coefficient, right, of this oscillator. So k should be positive or 0. That's the condition I have here on k. When we have a differential equation, we first start with, if you remember the first step I mentioned, we first have to start with the auxiliary polynomial. The auxiliary polynomial here, p of lambda, is lambda squared plus k lambda plus 9 is equal to 0. Okay? So we want to use the determinant given that it is a second order equation. So this is, discriminant is, remember, if you have a simple equation like ax squared plus bx plus c, the discriminant is b squared minus 4ac. So in this case, the discriminant is b squared is k squared, right, minus 4 times 1 times 9. So this is k squared minus 36. Now, remember that we generally treat this depending on whether the discriminant is positive, negative, or 0, right? So let's then go through all the possibilities. When it is given that we have k, we don't know the value of k. The only thing we know here is k, the damping coefficient, is positive or 0. So we have to play with the value of k. Depending on the value of k, this discriminant can be either 0, negative, right? And if we say negative, it means it will lead to complex values. It can also be positive. When it's positive, of course, there's no problem. Everyone is happy. Now, let's consider different scenarios. The first scenario is this. The first case, we assume that this discriminant is positive, okay? If we assume that k delta is positive, delta being positive means that it means k is greater than 6. So this is the first case. If k is greater than 6, then in this case the discriminant is positive, right? So we have two real and distinct roots. So we have two real and distinct roots because the discriminant is positive. And these roots are, let's call R1 the first root. It will be minus k plus square root of delta. So this is square root of k squared minus 36. All this divided by 2. And the second R2 is minus k minus square root of k squared minus 36 over 2. Then with these two, the general solution will be, so the general solution under this first case is y equal e to the power, let's say a times e to the power r1t. R1t is this term minus k plus square root of k squared minus 36 over 2 t plus b times e to the power r2. R2 here is minus k minus square root of k squared minus 36 over 2 times t. Let's put t out of the bracket. T. So in this case, A, B are real. So this is what we obtained for the first case. Now, for the second case, let's assume that the discriminant is equal 0. If the discriminant is equal 0, then k squared minus 36 is equal 0. This means k is equal 6. Because remember that we have this condition, k is strictly positive, right? Positive or 0. So in this case, if k is equal 0, then this R1 will be minus k over 2, and R2 will be minus k over 2. And in this, the general solution is very simple. It's just a, because we have double root here, right? A plus bt times e to the power minus k over 2t, with a, b in real. So remember, as I told you that this is just one way to write this type of solution when you have repeated roots. So you can write it in this way: y is equal a times e to the power minus k over 2t plus bt times e to the power minus k over 2t. So they are similar. As you can even see that this is just the factorized form of this second one, okay? Now let's look the last example, the discriminant. This is third case. What if the discriminant is negative? So we've started with discriminant positive, discriminant 0 for the second case, and now we are dealing with the last case when the discriminant is negative. If the discriminant is negative, it means k squared minus 36 is negative. So it means k, knowing that k is greater than 0, so this is the scenario where k is between this and 6. Okay? So if delta is negative, then k will be between 0 and 6. And this is complex. So this leads to complex root. We have R1 is minus k plus I square root of 36 minus k squared over 2, and R2 is equal minus k minus I square root of 36 minus k squared, all this divided by 2. So as you can see here, when the discriminant is negative, when this discriminant is negative, then it means that this can be written as minus, if you put the minus, we factorize the minus, this becomes 36, right? Minus k squared. So negative means that this term is positive, right? So that's why we have to swap the position of 36 and k squared here in order to get this form. And we know that I squared is minus 1, yes. That's why we have I here and I here. So the general solution in this case is y is equal a times e to the power, the real part here is minus k over 2 times cos of what we have here. This is square root of 36 minus k squared over 2 times t plus b times e to the power minus k over 2 sine square root of 36 minus k squared over 2t. Okay, so a and b are real. So this is the solution in the case of delta negative. Okay. Okay, this was a very technical example, given that you have to play with the value of k. That's why the question says describe the solution as k increases. So we know that k increases, k greater than 0, greater or equal zeros mean that k will move from 0 to infinity. So we have different scenarios. The first scenario is when k, the discriminant is positive. right? So generally, if you have a second order equation, we have to find the discriminant to solve that equation, right? So once you have a discriminant, you have different type of solution depending on whether the discriminant is positive, negative, or zero. Now that's what we have to go through. In the first case, we consider that the discriminant is positive and it leads to this solution. For the second case, we consider that the discriminant is equal to 0, and that's why we obtain this. As I said, these two solutions are equivalent. And the last case, we consider that the discriminant is negative. Being negative means that the k should be in this interval. With respect to this condition, k must stay in this interval. That's why we obtain negative root here, R1 and R2. And the general solution here is the complex form of the solution, as we know. Okay, this is all for this video. I guess it is understandable. A very good question. You can find this type of question in the exam. I'm not saying that is the question you will be part of your exam, but you can find this type of question even in the past question. You will be able to find this question. So yeah, this is all for the video. Thank you.